fizziness. Right? Liquid solutions, vapor pressure of solutions for liquids have physical properties that are significantly different than that of a pure solvent. So section 410. So example, antifreeze is added to water in a car's cooling system to prevent freezing in winter and boiling in summer. These preventative measures work because of the solute's effect on the solvent's properties. So when you mix salt and water together, you do not have the same physical properties of just pure water alone. Right? So that solute, we're going to look at two different cases where we've got a liquid solvent and a solid solute, like salt in water. And then we're also going to look at a case where we're mixing two liquids together. And how is that going to affect some of our physical properties like melting point, boiling point, and vapor pressure? Right? So if we look at an aqueous solution of pure water and pure water in a closed environment, so we've got water that's pure water and this aqueous solution, right? You're going to have an exchange of some of this water. And what's going to happen is nature kind of wants to seek a balance here. And so it can't move some of whatever was dissolved over to the other side. So it's going to try to make as uniform a solution as possible by pulling in water molecules. And eventually you'll be left with an empty beaker on the left, some water vapor up in here in equilibrium, and then this aqueous solution, which is going to absorb some of that water. So an aqueous solution of pure water in a closed environment, initially, right, we've got two beakers. After a period of time, the water is transferred over to the other solution. It's kind of like magic, but really it's science. Right? So we're going to start off by looking at the vapor pressures of solutions. So the presence of a non-volatile solute lowers the vapor pressure of a solvent. So if I've got this pure solvent, notice this guy is in here at 3. Right? I dissolve some non-volatile stuff in it, like sodium chloride. Pretty hard to get sodium chloride in the gas phase. Right? My vapor pressure is reduced down to 2. Right? I've got fewer of these red or green balls in solution. Right? So what is happening is that the dissolved non-volatile solvent decreases the number of solvent molecules per unit volume, and it should proportionately lower the escaping tendency of the solvent molecules. Now, this is not an exact analogy, but I'm going to give it to you anyway. So if I got little chunks of stuff on the surface here, they are effectively blocking one of these solvent molecules from being able to launch itself. So imagine, if you will, somebody is going up for a free throw and like this little yellow ball here is like, nope, and knocks that away. Right? So it's trying to escape, get into the gas phase, but that non-volatile solute is going to block access to that surface site. It's not a perfect analogy, but if you can keep it in your head that, yeah, if I mix something in there, my vapor pressure is going to go down, then I'm happy. So this brings us to what's called Raoult's law. Raoult's law says that the pressure of our solution is going to be equal to the vapor pressure of our pure solvent times the mole fraction of our solvent. So remember we said that mole fraction was going to be useful? This is where it's coming in to be useful. Right? So looking at a plot of our pressure of solution versus our mole fraction of solvent, right? If we start off with no added solution or no added solvent, right? Our mole fraction is 0, right? And we increase that over to 100%. So you can think of this as like 100%, right? 100% versus 0%. Then you're going from the vapor pressure of the pure solution to the vapor pressure of the pure solvent, depending on how far along you are. If you are at 50%, so 0.5, you're halfway in between the vapor pressure of your solvent and your solute. Yep. Let's look at an example. The Calculate the expected vapor pressure at 25 degrees C for a solution prepared by dissolving 158 grams of sugar, given this molar mass, in 643.5 cubic centimeters or milliliters of water. At 25 degrees C, the density of water is 0.9971 grams per cm cubed, and the vapor pressure is 23 torr. Right? So this is giving us part of our setup. That is the pure solvent and what its vapor pressure is. We know that our answer has to be less than this because we're adding in some solute. Right? So it's not going to be the vapor pressure of our pure solvent. It's going to be less than that. How much less? Depends on the mole fraction. Right? So in this case, our Raoult's law is that the vapor pressure of our solution, our mix, is going to be equal to our pure solvent times the mole fraction. To calculate the mole fraction of the water in the solution, the number of moles of sucrose and the number of moles of water have to be determined. So to figure out the moles of sucrose, you take your 158 grams of sucrose, divide by its molar mass, and you get 0.4616 moles of sucrose. You do the same thing for the water. You're going to convert that from a volume of 643.5 milliliters into a mass using the density. That's the Greek letter rho up there. So 0.997. We've canceled out our cm's cubed. We're left with units of grams. We've got 641.6 grams of water. Use that. And the molar mass of water, 18 grams, to get 35.6 moles of water. We now know how many moles of water. We know how many moles of sucrose. We can calculate our value chi. So chi is going to be our moles of water divided by our total moles. So 35.6 divided by 35.6 plus 0.4616. So 35.6 divided by 36.06, and we get 0.9873 is our mole fraction for the water. The vapor pressure is then just going to be our chi for the water times our initial vapor pressure, the pure water, and we end up with 23.46 torr. So we lowered it by 0.3 torr just by adding in just a little bit of sucrose. Right. Determination of molar mass is something we can do with the help of a phenomenon of lowering vapor pressure. Right? So this is one of those roundabout things that we can do with this information. Right? So one thing you're going to need to be able to do is this over here, right? Find the new vapor pressure. Right? This is kind of one of those stretch goals, right? This is what the CB student's going to do. This is what the AB student is going to be able to do. Determine the molar mass experimentally with the help of the phenomenon of lowering the vapor pressure. If you know the mass of a compound is dissolved into a solvent and the vapor pressure is measured, right? So you take some stuff, it's a mystery solid, you put it in to a container, right? And your vapor pressure, I'm going to try to draw a little gauge here, goes from 3 to 2. Well, you know how many grams were in here. You know that this new vapor pressure is going to be related to chi times your pure solvent's vapor pressure. You can figure out what the molar mass is because this chi has units that are going to be working in moles. And this over here, you know how many grams you put it in. If I want a molar mass, right, that is grams per mole. Since the mass of this number of moles is known, we can calculate the molar mass. And it's one of the ways we're going to characterize solutions. Yep. So let's do another example. We're going to predict the vapor pressure of a solution prepared by mixing 35 grams of solid sodium sulfate, 142.05 grams per mole, with 75 grams of water at 25 degrees C. The vapor pressure of the pure water at 25 degrees C is 23.7 torr. This is going to be our P0 or P0 value. We're going to calculate that mole fraction of water. So we're going to take our 175 grams of water, divide by the molar mass, or grams cancel each other out, left with moles of water. We're going to find the moles of sodium sulfate. We're going to take its mass, divide by its molar mass, grams cancel. We're left with moles of sodium sulfate. All right, we're going to find our, so it's essential for us to recognize that when 1 mole of solid sodium sulfate dissolves, it is going to produce 2 moles of sodium ions and 1 mole of sulfate ions. So if we think about what is happening, right, in our solution, right, we had all these water molecules. They wanted to get up into the surface, away from the surface, out into atmosphere, right? But now they're blocked by not just one thing, like we had with the sucrose. They're going to be blocked by 3 things, 2 sodiums and 1 SO4, right? So they're not going to be able to get out. The number of solute particles present in this solution is going to be 3 times the number of moles of solute dissolved. So our number of moles of solute is going to be 3 times the number of moles of sodium sulfate, so 0.738 moles. So our chi value is going to be the number of moles of water, at 9.71, and then on the bottom, our total number of moles is going to be the water plus all the moles of all the ions of our solute. And we end up with 9.71 divided by 10.458. So we end up with 0.929 as our chi value. Now we can use Raoult's law. We're going to plug in this value over here. We had our P naught value for the water of 23.7 torr. We end up with 21.2. And these are, notice, always are going down. The more solute you add, the lower it gets. The more things that solute can break into, the lower it gets. So 1 mole of sodium chloride is going to be more effective at lowering that vapor pressure than 1 mole of glucose. And 1 mole of calcium chloride, CaCl2, is going to be more effective than 1 mole of sodium chloride. So let's continue. Ideal solutions, a liquid-liquid solution that obeys Raoult's law. This ideal behavior for solutions is never perfectly achieved, but we can sometimes closely approximate it. Nearly ideal behavior is often observed when the solute-solvent and solute-solvent interactions are very similar. In other words, when like dissolves like. For liquid-liquid solutions where both components are volatile, that means they're both going to have some sort of vapor pressure, a modified version of Raoult's law applies, where our total pressure is going to be the sum of the individual pressures, the pressure from A and the pressure from component B. And the pressure from A is going to be the mole fraction of A times its pure vapor pressure of the pure solvent. And for B, it's going to be the mole fraction of B times the vapor pressure we would get for pure B. So P total represents the total vapor pressure of a solution with both A and B together, where they're both liquids, a little liquid. Where chi A and chi B are the mole fractions of A and B. P naught of A and P naught of B are the vapor pressures of pure A and pure B. And PA and PB are the partial pressures resulting from the molecules of A and B in the vapor above the solution. So here's a case where we've got A and B quite happily hanging out in solution. Right? Now, if your B, right, this B here is blocked by this A, just like it would be blocked by an insoluble sodium plus ion, or a carbonate ion, or a sucrose atom. So here, the A is blocking some of the B. And this B over here is blocking this A. So our vapor pressure for A will decrease, and our vapor pressure for B will decrease. In solutions where the solute and solvent are very much alike, the solute simply acts to dilute the solvent. If the solvent has a special affinity for the solute, they really like each other, then the tendency of the solvent molecules to escape is going to be lowered more than expected. So if there's a strong interaction, we're going to see a little bit of a negative deviation. The observed vapor pressure will be lower than the value predicted by Raoult's law. It's going to be a negative deviation. When a solute and a solvent release large quantities of energy in the formation of solution, so delta H of solution is large and negative, it can be assumed that strong interactions exist between the solute and the solvent. In this case, we expect a negative deviation from Raoult's law because both components are going to have a lower escaping tendency because they're going to still be attracted to that other stuff in solution. Right? A is kind of blocking you, but you're also kind of attracted to A, and you're like, well, maybe I don't want to go in the gas phase. If these two liquids mix endothermically, it indicates that the solute-solvent interactions are weaker than the interactions among the molecules in the pure liquids. Right? So this would be one that gets a little colder to the touch. In this case, the molecules in the solution have a higher tendency to escape than expected. They don't want to interact with each other. They want to get out. Right? They're repelling each other. And positive deviations from Raoult's law are observed. For a solution of very similar liquids, the enthalpy of solution is very close to zero, and thus the solution closely obeys Raoult's law, which we call ideal behavior. So these are two cases and our ideal case. So in an ideal case, we have this partial pressure of A, right, as we go from 0% A to pure A, and a partial pressure of B as we go from 100% B to 0% B. Right? Our vapor pressure is going to be the sum of those two. Right? So our green line here is going to be our what we would expect to calculate from Raoult's law. Over here, where we've got a weak solute-solvent interaction, right, they're going to repel each other. We're going to have this positive deviation of bowing out, a little bit more pressure than we expect. In the case where they're strongly attracted to each other, like say glycerol and water, which have a lot of hydrogen bonding, we're going to have this negative deviation. We're getting less pressure out than we expect. So, summary of the behavior of various types of solutions. So, the interactive forces between the solute and the solvent particles. So, if we're looking at A interacting with A and B interacting with B, and they're about equal to the interaction between A and B together, our enthalpy of solution should be zero. Our change in temperature should be zero. We're going to have no deviation for Raoult's law. Right? So, benzene and toluene is a great example of that. And just London forces, no real attraction between B for A or A for B. They're all on the same order of magnitude. If we have the interaction between A and itself and B and itself as being less than the interaction between A and B, right? So A and B are attracted to each other. It's going to be negative or exothermic. Our temperature is going to increase. It's a positive change in temperature. We're going to have that negative deviation from Raoult's law, right? Because they're still attracted to each other. So, for example, acetone and water, right? If we've got A and B, so the AA and BB interactions are about the same, but they're bigger than the interactions between A and B. So A likes to hang out with B likes to hang out with B, but A and B do not like to hang out with each other. That's going to be a positive or endothermic mix. Our temperature will drop. Our deviation will be positive, so something like ethanol and hexane, right? These are opposite. They're not going to want to mix with each other, right? Acetone and water, both are going to want to mix with each other because they're polar. So let's do a quick concept check. For each of the following solutions, would you expect it to be relatively ideal with respect to Raoult's law, show a positive deviation, or show a negative deviation? So let's do number one. Okay? Hexane and chloroform. Pause and think about it. Right? That's going to be an interaction where you've got something that is nonpolar and something that is polar. So we're going to be over here, right, where we've got an interaction like this. It's going to be a positive deviation. Right? Let's look at the next one, ethyl alcohol and water. Pause, think about it. Okay, if I've got ethyl alcohol, that can undergo hydrogen bonding. Water can undergo hydrogen bonding as well. They're going to be attracted to each other. It's a case like this. There's going to be a negative deviation for Raoult's law. Right? They're still attracted to each other. The water and the ethanol are attracted to each other, lowering that vapor pressure more than expected. What about hexane and octane? Pause. Think about it. Okay, we've got London forces for the hexane, London forces for the octane. This is very much like this benzene toluene case. It's going to be pretty close to ideal. Let's do another example. We've got a solution containing two liquids. We're going to mix 5.81 grams of acetone. It's given us the molar mass, and 11.9 grams of chloroform, given its molar mass. At 35 degrees C, this solution has a total vapor pressure of 260 torr. Determine if this is an ideal solution or not. Just kind of looking at it, we see acetone, which we know is going to be polar, chloroform, which we know is going to also kind of be polar. So we're going to expect some probably negative deviation, but let's look. So the vapor pressure of pure acetone and pure chloroform at 35 degrees C are 345 and 294 torr respectively. We're going to need to use that version of Raoult's law where we're looking at the P total as being the sum of chi A times its pure solvent vapor pressure and chi C for the chloroform times its pure vapor pressure. A is for the acetone and C is for the chloroform. The calculated value is going to be compared with the observed vapor pressure, right? So they said beforehand, right, we experimentally measured it to be 260, right? It's going to deviate. So we'll take our grams of acetone, use the molar mass, and we'll get moles of acetone. We'll take our mass of chloroform and its molar mass, and we'll get our moles of chloroform. Since the solution contains an equal number of moles of acetone and chloroform, chi for A is going to be 0.5, and chi for the chloroform is going to be 0.5. So if you wanted to work that out, right, it's 0.1 over 0.1 plus 0.1. Right, 1/2. The expected vapor pressure is then going to be chi A times the vapor pressure of pure acetone, and chi for the chloroform times the vapor pressure for the pure chloroform. So 0.5 times 345 plus 0.5 times 293 gives us 319 torr. So our observed pressure, 260, is less than our absorbed 319 torr, right? Which indicates the solution, one, doesn't behave ideally. It's a negative deviation from Raoult's law, which can be explained in terms of the hydrogen bonding interaction, right? We've got this acetone. We do have an oxygen with some lone pairs over here. It's going to try to grab this guy. It's kind of a weird case of hydrogen bonding, but you could still have a polar-polar interaction, right? So there's still going to be forces of attraction.